Hi, this is Gary Gigabit Gumenow. Thanks for joining and taking a closer look today at the new Intel innovation called Application Device Queues, or ADQ. I'll be demonstrating Application Device Queues and how it helps a Redis database. ADQ is the latest feature enabled on the Intel Ethernet 800 series network adapters and Ethernet controllers. ADQ provides dedicated hardware network device queues for exclusive use by targeted applications and to optimize efficiency of packet management by the Linux kernel. Think of it as a dedicated express lane on the freeway for critical applications traffic. Redis is an open source, in-memory data structure store used as a database, cache, and message broker. Today it's used by companies such as Twitter, GitHub, Airbnb, and so many more. We're going to compare Redis performance when the network adapter uses ADQ versus default baseline configuration. We'll compare average latency, transactions per second, and predictability on different load conditions. The goal of ADQ is to ensure that high-priority applications receive optimized performance through dramatically reduced latency, improved predictability, resulting in higher network throughput, especially on very parallelized workloads. As a data center grows with more servers, jitter increases with scale, resulting in application transaction outliers in an otherwise fast system. The larger the data center, the more critical predictability becomes. If application transaction predictability cannot be controlled, it can hinder the ability to scale out that application in a very large data center. With indeterministic predictability, the user experience will be impacted because the expected response time is erratic. Let's take a moment and describe what we're seeing on the screen. Two charts on the top are showing average latency and throughput. These are known to be the most adopted quality of service or QoS measures. The left chart is showing predictability, which I'll cover in a moment. On the menu, I can change the number of connections from 22 to 8800, representing low, medium, and high traffic on the system. Average latency measured in microseconds shows packet average traverse time from the interface at the network adapter up to the Redis application. For example, 2200 connections. Non-ADQ system, here in red, shows average latency around 320 microseconds. At the same time, an identical system equipped with ADQ's express traffic lanes, here in blue, shows average latency around 150 microseconds. Conclusion: ADQ provides evident average latency decrease for a prioritized Redis application of about 50 to 60%. Throughput shows completed transactions per second. Non-ADQ system shows average throughput around 6.3 million transactions per second. At the same time, an identical system equipped with ADQ shows throughput around 10.6 million transactions per second. Again, ADQ provides evident transactions per second increase of about 65%. When we increase the number of connections, we could observe just a slight increase in average latency for ADQ and dramatic latency increase for non-ADQ systems. With larger workloads, ADQ proves to be even more efficient. Throughput shows a constant gain of 65% with ADQ enabled, regardless of the number of connections. System performance has traditionally been measured in terms of latency and throughput. As data centers scale, a third metric becomes increasingly important: predictability. Predictability, or jitter, is the variation in turnaround time when a response will be received. As a data center grows with more servers, jitter increases with scale, resulting in application transaction outliers in an otherwise fast system. The larger the data center, the more critical predictability becomes. If application transaction predictability can't be controlled, it can hinder the ability to scale out that application in a large data center. With indeterministic predictability, the user experience will be impacted because the expected response time is erratic. A predictability graph shows how many connections complete in a given time. For ADQ, in the blue, we can observe the far most connections complete in 300 and 400 microseconds, and the whole graph is very slim, meaning all connections complete in more or less the same time, so high predictability. For baseline, in the red, we can observe the graph is dramatically wide, flat, with evident tail latency. We notice discrepancies between fastest and slowest response. It's hard to determine true job completion time, thus low predictability. To visualize it better, we can apply the 99th percentile measurement. 99th percentile estimates the completion time for split jobs and is also a base for service level agreement contracts. For 99th percent of connections, ADQ-equipped system returns 500 microseconds, whereas baseline system is huge at 900. When we switch to 6600 connections, there is again high and slim predictability for ADQ and very flat and wide for baseline. ADQ's 99th percentile here is 700 microseconds, and baseline is so bad it falls off the graph completely. It's over 1,000 microseconds. When the job is split and sent to threads under large jitter, it will be hard to predict how fast the entire job is completed, meaning low predictability. You can compare this to taking kids to a zoo. When it's time to go, it doesn't really matter how fast the quickest kids get on the bus. The bus won't leave until the last kid has gotten on. If the first and last kids board at more or less the same time, we get high predictability of departure time. If the entire class has boarded the bus except for that one kid, the departure time will be delayed. The same is true in large-scale applications. It is not essential how quick the fastest task is completed. It's the slowest ones that dictate the overall system performance and predictability. This demo aims to show at scale, low latency and high throughput is not enough. Predictability is also required. Predictability, which is opposite to jitter, not only supports scalability, but also enables more compute servers to be assigned to a task and can allow more users to access the system, providing a better end-to-end user experience, better utilization, and lower costs. For real-time applications, the key is latency and predictability that enable improved throughput. In the past, ensuring predictability was accomplished by over-provisioning hardware, which is extremely inefficient economically. ADQ provides performance with controlled investment. By dedicating network adapter silicon hardware to high-priority applications, the Intel Ethernet 800 series with ADQ prioritizes network traffic for greater predictability, improved responsiveness, and higher throughput from the edge to the cloud. Greater predictability and responsiveness to customers can lead to higher satisfaction and retention. This may provide cloud service providers with a competitive advantage and improved value proposition to a wider customer base. This demo shows the impact of ADQ's express traffic lanes to performance of Redis application, improved network performance and application response time predictability for key cloud applications, including web tier, caching, and databases. Where applications are the most evident beneficiaries, I believe that ADQ is equally useful technology for service providers, where it gives a base for more compute servers, more users, more optimized applications, and premium service level agreements, all at the cost-efficient manner of Ethernet. So thanks for coming and checking out the Application Device Queues demo. This is Gary Gigabit Gumenow. Until next time.